Linear regression from scratch. If the programming language you are using does not have a function for the linear least squares regression, how would you design an algorithm to do so? Alright, let's start by writing our linear equation as a reminder. For a given observation or sample I, we can write yi is equal to beta 0 times xi0 plus beta 1 times xi1 plus etc. up to beta p minus 1 times xi p minus 1, where I goes from 1 to n, so we have n observations. A typical example to explain this equation is the housing prices. So here yi will be the house prices and the xi will be the features of the house, say number of bedrooms, kitchen size, proximity to schools, etc. And the parameters beta represent how much each of these affect the prices, and that's what we want to find out. Here xi0 is always going to be 1 so that we can have the intercept term. By the way, we call it a linear model because these features represented by xi are linear. If you have some non-linear features, say x squared, then you can square it beforehand and still treat it as a linear feature. Now, depending on the background of the interviewer, they might use a different specific jargon for x, y, and beta. So that's why it's good to be familiar with the nomenclature. The x, y might be called explanatory variables, predictors, independent variables, regressors, covariates, exogenous variables, features, inputs, or attributes. The yi's could be called response variable, dependent variable, outcome, endogenous variable, target, label, output, or true value. The betas might be called regression coefficients, parameters, slope coefficients, or model weights. And finally, the epsilon could be called error term, noise, or residual. Again, the goal in linear least squares regression is to find the beta parameters by minimizing the cost function that is the sum of squared errors. One valid way, but probably not the best way, is to use the gradient descent. To do so, we again set up a cost function j beta similar to the above. Here, the yi's are the true values and the hi's are the model outputs. The derivative of this with respect to specific beta j will look like this, where it picks out the xj. Then we can iteratively update the beta j using that derivative and some hyperparameter step size alpha. So why do I say that this is probably not the best way for a given problem? Well, you have to judiciously choose the step size alpha and set up the initial values, which takes human time. Also, it might be quite slow as it is iterative, and reaching the global minimum is not guaranteed, so we are not necessarily getting the exact solution. If you are being asked this question in an interview, they probably want you to derive the normal equation, or at least know the answer off the top of your head. So let's derive the normal equation and solve it using the direct matrix inverse approach. Once again, the yi can be written as the sum of xik times beta k, where k runs from 0 to p minus 1. So p is the number of beta parameters, and we'll have n observations. We can actually rewrite the above in matrix form simply as y is equal to x times beta plus epsilon, where the capitals now represent matrices. Here, y will be a skinny tall matrix of size n by 1, x is going to be of size n by p. Again, remember that the first column of this matrix is going to be just ones. And by the way, this matrix is sometimes called the input or design matrix. Next, beta is going to be a tall skinny matrix of size p by 1, and finally epsilon is of size n by 1. Now, to be able to minimize the error in the matrix form, we will need some matrix calculus derivatives. There is an extensive wiki page on this, and the rules depend on whether you use a numerator or denominator layout. Here I'm using the numerator layout. So we'll need three derivative rules here for matrices A and X. One is dAx over dx is equal to A. Second, dx transpose A over dx is equal to A transpose. And finally, dx transpose Ax over dx is equal to x transpose times A transpose plus A. Now let's minimize the cost function with respect to beta. Note that this can be written as y minus x beta transpose times y minus x beta in matrix form. Expanding this out gives us 4 terms, and let's call this L beta. And we're looking for d L beta over d beta. Let's go term by term for the above 4 terms. The first one is just 0 since there is no beta in here. For the second term, we use one of the derivative rules. Similarly, for the third term, we again use one of the given rules above. Note that transpose changes the order in matrix multiplication. Finally, the last term uses the remaining derivative rule. Now we say that the derivative of the cost function should be 0 and put all the terms together. Let's take the transpose to get beta instead of beta transpose. Multiply by the inverse of x transpose x from the left on both sides. This gives us a closed form solution for beta known as the normal equation. Note that even though X is a non-square matrix, X transpose X is a square matrix, so we should be able to take the inverse of it. For example, one can use the Gauss-Jordan method to take the matrix inverse. Once we solve for beta, we get an exact solution as opposed to the gradient descent. However, direct matrix inverse approach is generally not recommended as it is known to be numerically unstable. It's said that X transpose X squares the condition number. But it should still work if this matrix is not ill-conditioned. To demonstrate that, I have provided a GitHub link in the description below if you'd like to see a from-scratch implementation of this in C++, including matrix element getters and setters, matrix multiplication, transpose, and inverse using Gauss-Jordan method. Basically, this mini project is a minimal linear algebra package with a working linear least squares regression. Alright, coming back to the normal equation, is there a more numerically stable way to solve this? Actually, one can use the QR decomposition. QR decomposition tells us that if you again have a square matrix A, then you can express it as a product of two matrices Q and R. Here, Q is an orthogonal matrix, so we have Q inverse is equal to Q transpose. And R is an upper triangular matrix with positive diagonal elements. Now, above we derived that X transpose X times beta is equal to X transpose Y, but now we can think of this simply as A times beta is equal to B, where A is a square matrix, so we can apply QR decomposition. Then we get QR times beta is equal to B, and multiplying the left side with Q inverse gives us R times beta is equal to Q transpose times B. Now, this can be solved recursively starting from the last element of R and working our way back. This QR approach also gives an exact answer, unlike the gradient descent. It's also more stable than the direct inverse of normal equation. However, there's an even more stable method, and that is the singular value decomposition, or SVD. An advantage of SVD is that it can work with non-square matrices. So if we have a general X matrix, then SVD tells us that we can express it as a product of three matrices, U, sigma, and V transpose. U and V transpose are unitary matrices, and sigma holds the singular values in the diagonal. It kind of looks like eigen decomposition, but it's different. Now, although X does not have an inverse in general, we can get a so-called pseudo-inverse, which is V times sigma inverse times U transpose. So we initially had Y is equal to X beta, where X was a non-square n by p matrix. Then it can be shown that beta is equal to X pseudo-inverse times Y minimizes the L2 norm, which is what we want in least squares. This approach is known to be a very stable approach. It gives exact results, but you can also get approximate results by truncating the small singular values below some threshold. SVD is a huge topic and it's used in so many applications. So it's not possible to fully cover it here, but I recommend the video series on SVD by Steve Brunton from University of Washington. So overall, deriving the normal equation and briefly explaining the QR and SVD approaches should be sufficient for an interview question.